It is. So the first part of this course is going to be about conformal field theory in higher than 2 dimensions, and the reason is I think most of you know. And we will be on the first thing to learn about conformal field theory is that 2 dimensions are really special dimension as far as conformal field theory goes. Also for standard quantum field theory, but especially even more so for conformal field theories. So the reason, the first thing we must motivate why we study conformal field theories. So, you can read any of those reference, much better motivations and examples of conformal field theories where they arise in physics. I will just give one of those examples really quickly, which is we have, you all know, I'm just thinking, you all know that conformal field theories do not have a mass, a length scale or a mass, because a mass will set up a length scale due to you can build a Compton wavelength, which would break conformal invariance. So scalar invariance, if you do not have a scalar invariance, you do not have conformal invariance. And there is a difference to learn about it. So you can ask, so a conformal field theory has scalar invariance. It looks the same at all energy scales. So why do we study? Isn't that this too special? For in particle physics, we know an electron has a mass, and we have lots of length scales. We have electron mass, we have proton mass, we have Higgs mass, have supposedly a Planck scale. So it would seem it doesn't make much sense to study conformal field theories in high energy physics. Conformal field theories first appeared in the context of, as far as I know, I'm not a specialist, in the context of statistical mechanics and condensed matter systems, studying spin chains or things like that, Ising models in 2 dimensions. And the thing is, for a special value of the parameters, like temperature and so on, the system displays conformal invariance. The correlation length blows up, goes to infinity, and you have an effective theory which enjoys conformal invariance. In particle physics, or in any, let me just speak about any quantum field theories. We have the renormalization group. And just as a disclaimer, warning, we will not use, except for its motivation, the ideas of a normalization group. If you haven't studied a normalization group, there's no problem. You won't miss anything. So for the motivation. The normalization group tells us that we have a space, and in fact, an infinite dimensional space. You could label these axes by the coupling constants of the theory, Lagrangian. So we can have infinite axes, infinite dimensional space. And the normalization group says each point in this space is a quantum field theory. It's characterized by some given values of all its coupling constants. And the normalization group tells you how to relate different quantum field theories in this theory space or Lagrangian space or whatever you want to call it. And you have what we call a flow between these quantum field theories by doing a normalization group transformation. What you're doing is just, the normalization group idea is just like the most efficient way to implement renormalization in theory. It gives a more physical picture of what's really going on. You're just not like throwing out to hide infinities under the rug, things like that. And there are special points in this, which I kind of drawn here already. There are some special points in this theory space that we call fixed points. It is a point where, when you hit that point, you start from any quantum field theory, say here, and you follow the flow. you compute the beta functions and so on. You will eventually hit, supposedly you can find fixed points. The fixed points. On these fixed points, you have, by definition, the beta function is 0. The beta function of all the copies. Everyone knows what a beta function is. Have an idea? It just tells you how your coupling constants are varying according to scale changes, right? The energy scale. And so by definition, when the beta function is 0, it means your theory, once it hits a fixed point, it will be you will have scaling invariance. Usually, for given a set of hypotheses, which we'll talk about later in another lecture, but those involve things like Lorentz invariance, a discrete spectrum, things like that. This scaling invariance is enhanced to conformal invariance. Which is a stronger version of scaling invariance. And this is actually a CFT. For the scaling invariance, if you only have scaling invariance, some people call it scaling field theory, or SFT. And it is a subject of ongoing research when scaling invariance implies conformal invariance. There is a theory for 2 dimensions. It is the Zamolodge, something like that. I don't know what's the name. It's a Zamolodge theorem, and it says under which conditions on 2 dimensions, scaling transformations, scaling invariance becomes conformal invariance. Any questions about this? I just focus on the idea.
There is some configuration of coupling constants for which the theory becomes conformal field theory.
Yeah. In principle, scaling field theory, but usually.
But at the fixed point, it becomes a conformal field theory.
Yeah, the fixed point of theory becomes a conformal field theory. Once it reaches the fixed point, we'll sit there and won't vary anymore. If you keep doing analyzation of transformation at the fixed point, we won't move. Any more questions? Okay, so this is the way that conformal field theory can arise in a general quantum field theory. And there are arguments that show that any quantum field theory can be understood as a point along this flow between 2 conformal field theories. Ideally, you have a ultraviolet CFT for really high energy scales, and this CFT flows to a CFT in the infrared. And then standard quantum field theory would be these points along this flow. And since conformal field theory, since it enjoys more symmetry than standard quantum field theories, what happens is that we can constrain much more conformal field theories. And we can imagine starting at a conformal field theory and perturb the conformal field theory by hand, introducing some operators that will explicitly break conformal invariance, which means that we will trigger a flow in the theory space, and we'll find a set of quantum field theories that lie along this flow. So we can, by understanding conformal field theories, we can understand by this idea. We're using this idea, we can understand all the standard quantum field theories. Right? This is kind of the idea of universality that one comes across when studying a normalization group. You can have lots of quantum field theories that correspond to the same conformal field theory, either in the infrared or the ultraviolet. And the idea is, typically quantum field theory here, we have a length scale, but in the infrared, it might be energy scales low enough that we don't see the length scale. We're below the length scale. Say we have QED. We have the. Let me just make a disclaimer. QED is not conformal invariant, but for the sake of the argument, suppose it is. We can imagine we sit at an energy scale below the electron mass. So we do not excite any electrons. We only have photons. So we don't see the length scale. So it could look conformal invariant. It will not be conformal invariant because we will see technically how to tell whether a theory is conformal invariant or not. But the length scale from the electron mass disappears because it's sitting below it. We won't excite any electrons. By the same token, we can imagine if we go to high enough energies, our length scales will be negligible. So we will have a CFT in the ultraviolet and a CFT in the infrared. There is one paper, I guess. If anyone wants to take a look, but it's more advanced, use more advanced ideas. And they prove that for any quantum field theory, in I don't remember all the hypotheses, but I guess they prove it for 4-dimensional, 3 plus 1 or Euclidean, I don't know. That the asymptotics of all consistent quantum field theories will consist of a conformal field theory in the ultraviolet and a conformal field theory in the infrared. And this paper is called the is by Lucy. Polchinski, That's it. To prove this, they use more advanced ideas inspired by string theory and things like that, but there is a general. There is a way to make these ideas precise, right? I'm just not going to them here. We're going to learn the basics. We have limited time, so you're going to learn the basics about higher two-dimensional conformal field theories in the second half, and higher than two dimensions conformal field theory. Any questions? Okay, so let me just. Before actually starting the course, so let me just remind you what we do in standard quantum field theory. We usually say, okay, we have in nature we observe Poincare invariance. We only have a process that preserves both length scales and shapes, angles. So we demand that we have Poincare invariance. Right, let me put it another way. We demand that we have the lengths are preserved. What this means? It means that we have a metric, any metric, it doesn't have to be Minkowski.
The length in space-time.
That's in space-time, yeah. Space and time. To be able to
The interval.
yeah. Maybe it will be better. Intervals are preserved. This means that a metric under some transformation it will be preserved. Say. The transform metric will just be our original metric. When we work out this condition, we find what we call the Poincare group. Which consists of translations and rotations. And by rotations, I'm including in rotations Lorentz transformations. Just like rotations around the time axis. These transformations, again, they preserve length because they do not change the metric. And then what we do, we say, okay, we want this, this is standard quantum field theory. And then we say, we want this symmetry to show up in our Hilbert space. And we learned that the way to do this is to introduce, to implement these symmetries as unitary linear operators or anti-unitary anti-linear operators. And then we classify our states on our Hilbert space by the momentum. Or eigenstates, at least if we have a free theory, they are this momentum operator, this is the momentum itself, they are the eigenvalue. And we can have this is for scalar particle, just ignore spin. But in general, we will classify our states by their momentum and spin. They also have a mass, we measure a mass. If the theory has massive particles. And one important thing that is really particular to standard quantum field theory is that we have a particle interpretation. This means that you start with free theory in course, and you see that for free theory, your eigenstates Fock eigenstates. That means you can count precisely. Okay, I have one particle with this momentum, this spin, this mass in this state. I mean, this is the state. So we can count. We have one particle here, say 5 particles here, 20 particles there, no particles over here, and so on. This theorem is a hard theorem, I guess, from theorem. And when we move to an interacting quantum field theory, there is, I guess this is the hard theorem. It says that the eigenstates are not particles anymore. What they are, I don't know. No one knows unless maybe for some really special cases, maybe in 2 dimensions. Because more special can do more things. But what we usually do then, when you work in perturbation theory, we say, okay, my interaction is really weak, so I imagine, though I don't have particles, I can imagine that it is not too far off from particles. And when we go to interacting, use interactions, we can in a way keep the idea of particles, but the price it pays is that these particles can go off shell. So this leads to the final diagram, say. For example, something like this. This would be, say for QEDs, would be electrons, photons, whatever. And this photon would be an off-shelf photo, it would have mass or whatever. It would integrate over all momentums here in the loops. And the reason, say conceptually, is this one. Eigenstates, we don't know what they are, but the interaction is weak. We can still keep the particle picture, but we have to put these particles off shell and we can work out the perturbation theory and everything looks how beautiful. But now for any question about this? Everyone has seen this. This is like a light review of quantum field theory 101. That's what's that takes an entire part 1 quantum field theory lectures. For conformal field theory, and from now on I will just write CFT as I did that. There was one major difference is that, well, what do we demand? We no longer demand that lengths be preserved. We demand that shape or angles are preserved. This is a weaker requirement, right? Of course, if I preserve lengths, I also preserve angles, but if I preserve angles, I not necessarily preserve lengths. And the form of the change in the metric takes this into account is if I do a conformal transformation, the metric will change up to a scale factor that in general can depend on the position. But this metric here is the same as this, just a scale factor. And we will see, we work out we do the computations, we see that we have just a constant. If this scaling factor, this is called the scaling factor. If this scaling factor is just a constant, this is what we call a scaling transformation. What this does is you just like you're zooming in and out in your space time. Say if you have, I don't know, a square, then you apply a scale transformation, you just end up with a bigger square or a smaller square. But what you're doing, you're either dilating or contracting all your lengths simultaneously, right? You cannot. This wouldn't be a scaling transformation. Right? You have a square and you just say scale one distance. This is not a scaling transformation. Scaling transformation, it is a constant. You just scale everything at once. And this is the only one, let's say, intuitive transformation that preserves angles, but it turns out that there is another one when this is in fact position dependent, and this is what we call a special conformal transformation. It's hard to imagine what this does. But we will see that first. We will see that if the rigorous comes out of the calculation, this transformation must be there. And what it does, like, I'll try it, but I'll probably fail. So you have I don't know, in the Euclidean space here, you have these grids. What do you do? Like, you start to curve these things. I don't know. It allows for things like that, as long as, say, all these angles are right angles. Alright, maybe it clear, but we just curve your space in a way that still preserves angles. It will be like, in a certain way, this local scaling transformation. So, like you're making different scaling transformation at each point.
Are you
That we will. Sorry.
I think you can imagine like the complex plane.
Yeah, exactly. It shows up the complex.
function is actually
This fact will import for two-dimensional conformal theories. It is part of the reason why they are much more special than higher dimensional conformal theories. But you also learn a more intuitive way to think about this special conformal transformations, which is called SCTs. From now on, special conformal transformations. We'll see more intuitive way to think about them when we actually start to get into the computations. But for now, just think like some space-time dependent scalings. Okay, so what happens when we play the same game here? We say our Hilbert space, I want my Hilbert space to have conformal symmetry instead of just point-ahead symmetry. Well, many things happen, but I will just tell you guys one of them that's the most constructed. This one, we will learn that in conformal field theory, particles do not exist. Why? What is a particle? Conceptually, it is a lump, it's a localized lump of momentum, energy momentum, spin or whatever. And if particle exists, then you surely break conformal invariance, or at least you break a scaling invariance. At the very least, this wouldn't work if you try to build a SFT, scaling field theory, inside the conformal field theory. And the place where this to look. Where this technically where this shows up is in the I'm guessing how to write this thing. I guess it's like this. Challen-Lemon representation. I mean, everyone already taken notes of this. Can I also raise this one? Right? Let me just to make this point more clear. When we have a standard quantum field theory, we have this, for any field theory, we have this Challen-Lemon representation, or spectral representation. It is a general way to write your 2-point function. Your final propagator is the time order product, so here just consider scalar for simplicity. The spins won't matter for this argument. There is a general way to write this, a non-perturbative way, it doesn't depend on constellation theory, which is and just already like second away from the electrons I prepared, but something like, don't take this too seriously. I might be missing some things here, but in general you have integral over momentum, say for dimensional, can be for d-dimensional pictures. And you have what we call a spectral density function here that depends on your b square, this is an invariant. And you turn out you have in general something like this. You have the final propagators here, and you're integrating over momentum. Let me just send these, maybe some different. might be missing something here, but what is important is that for standard quantum field theory, for free theories, most importantly, when you have particle interpretation, how do we see these particles arising? We look at the poles of this propagator. We see that we have a pole at plus or minus m. And we identify this as, okay, we have a particle of this mass, in this case they are our scalars for simplicity. We have a pole at this value of m, of p. And this, you can show, implies that the spectral density function will have a delta. It will be something proportional to a delta function plus some other things. So what this is telling you is that you have, this is a precise statement that's telling you that you have a particle of mass m in the spectrum of the theory. This is a exact result. And you can do this again by looking at the pole propagator. Here in these dots, usually you could have for more complex theory, complex in the sense that you could have other poles, you could have other poles here, you could have more propagators and so on. And you could have more particles here, and eventually you would have a branch cut, you would have a continuous. Alright? Everyone has seen that before? No?
Just conceptually.
We're not, this won't be, again, just like, this won't be too much important.
But I get it.
We still want the motivation here.
Yes,
right?
completely clear.
I just want to make this point more clear. What happens in conformal field theory is that, well, what we do with this, we say in standard conformal field theory, before moving to conformal field theory, maybe this will make things a bit clearer for you. We have, what experiments do? We imagine we have three particles here. Three particles here. These are the in states, these are the out states. Meaning this region is time tending to minus infinity, and this region is time tending to plus infinity. We say that standard quantum field theory, we imagine our interactions died asymptotically. And if we have a field theory there, we can give a particle description to this theory. And this is what this captures. We won't have a delta here. Our particles are all far away from each other, not interacting. I evolve time, and at some point here they will interact. When they interact, I don't know what's going on there exactly. In perturbation theory, we have some idea, of course. But in general, we don't have much idea what's going on inside here. But then we imagine that as we keep evolving time, the interaction will take place, and then they again die off in the asymptotic region, and end up with a different set, in general, a different set of free particles. And these guys are what we imagine. But in a conformal field theory, or just a scaling field theory, this cannot happen. And this is what defines as the S matrix. Right? The S matrix is just the matrix that evolves these states into these states. And in a conformal field theory, or just a scaling field theory, this cannot happen because, well, if you have a free theory, you have a free conformal field theory, then you can do this. It's free, but it's trivial. It's not much exciting. But if you have an interacting conformal field theory, then as we send the time to minus or plus infinity, so we go to a asymptotic region, if the theory is indeed has scaling invariance, they will keep interacting. You don't have this picture anymore. So this is one first things about conformal field theory that you should be aware of. You don't have S matrix in CFTs. Unless, again, it's a free CFT with massive particles, then, but it is just trivial. More interesting conformal field theories don't have S matrix. And a consequence is you don't have particles as well. So we won't, in any point in these lectures, be using finite diagrams, for example. It is not using conformal field theories. It's not a useful concept. Alright, that's it. There are any questions about this? The ideas are clear? Alright. And what happens, just to close this, what happens in the for conformal field theory? Not only a conformal field theory, but understand the interactive quantum field theory when you have the interactions switched on. If you're doing renormalization or normalization group, we will have this thing we call anomalous dimensions. We have to renormalize the wave function itself. We have to what happens is, say you have a Lagrange here and you have a scalar. And if you have interactions, usually you have to renormalize this guy here. For free theory, it will just be one. You just normalize, okay, it's one. But if you have, of course, you have more things here. And what this implies, when you study renormalization theory and normalization group, this will give an anomalous dimension. For the field. Everyone knows what I mean by dimension, right? Just like I say, this four-dimensional theory, then the derivatives have mass dimension 1, then the fields squared should have mass dimension 2, so the field has a mass dimension 1. So for free theory, free scalar theory here in this example, we have mass dimension 1. And for any free theory, in any free theory, for instance, scalar free field theory for fermions and gauge theory, if they are free, then this k dimension will either be in general like just an integer or a half an integer. And what this will imply for this Aula representation is that you have like just this structure. You have b squared minus m squared here. But what the anomaly is that if you, in the interacting regime, you get this anomalous dimension. And what this will do is you make your field have some corrections here. And this will in turn, in general, be just like any real number.
Can you repeat when does that happen?
What happens?
This behavior.
This?
Yes.
If you have interactions. If you're doing, if you're normalizing your field, you have to normalize its wave function. And what this implies is that it will move, it will change the mass dimension of your field. So we start with the classical field theory, classical scalar field theory, then the scalar has mass dimension 1, and we can interpret that as being a particle, mass m, and so on. But if we switch to interactions, and we're not in this asymptotic regime, we're just sitting somewhere here, during the interactions, what happens is that this will make a shift in its mass dimension, and it will not be an integer or half an integer. It will be any real number in general. And what this implies, you won't have this anymore. You won't have a nice p squared. You have some delta here, or any real delta. And then what? You have a branch cut, right? You can, for any non-integer power here, we can write this as exponential, exponential logarithm, and all that. And the logarithm, has a branch cut. And so what happens is that you won't get any delta functions here the spectral density. You only have a continuum. So the reason I'm telling you this is because particles do not exist. It usually said that in conformal field theories, people say, okay, conformal field theories do not have length scales. So there cannot be massive particles in conformal field theories. And I say, okay, that's right. You cannot have massive particles in conformal field theories. But it's more due to the fact that they would be particles rather than they would be massive. Alright? Because you do have massive modes in your field. We'll learn about that. What you cannot have are particles. Unless again it's a trivial conformal field theory, massless particles, and everything is trivial. So we will not ever talk about particles in conformal field theory. We won't ever talk about Feynman diagram and things like that. You will employ other tools for this. Alright, is that clear? It's a bit unusual from what we usually do in standard quantum field theory, but the thing is we get too addicted to that framework. But I hope the idea is clear, why none of that will show up here. If you try to keep thinking about conformal field theories, if you try to keep thinking about, let's try given a particle interpretation, we just keep running into contradictions. It's not a useful concept. That's why I'm telling this to you right now. We'll get to all these results, basically. I mean, I won't compute the spectral density functions, but we will do, we'll compute the propagator, and we'll see these anomalous dimensions, things like that.
So if you don't have particles, when you try to build from conformal invariance, you do the Wigner analysis and try to find the representations.
Yeah, we will do that.
Representation space.
We will do that.
The space does not have. It's not a square integral, or is it?
What do you mean by?
No, because the particles is a lump of momentum.
Yeah.
You say that in conformal field is not that. Therefore, you can't call it.
Yeah. What happens in standard quantum field theory?
So the Hill space is not the wave function is not. It does not decrease fast like a square integral.
Yeah, maybe you can. I never thought about this like this. Maybe you can think about this. But what is closer to representation theory, as you said, is that in a standard quantum field theory you just label your states by the momentum. And you have the Casimir operator, you have two, you have one that's related to spin, you have one that is related to mass. It means you can measure mass, because you can use it all, it's a Casimir by definition, you can use it with all other operators, you can use it with the Hamiltonian and so on. And this mass sets up a length scale, so you cannot have scaling variance. In a conformal field theory, what removes this length scale is that the mass square won't be a Casimir anymore. We have other Casimirs. So, at any given state in a conformal field theory, if you just think about quantum mechanics, it will be a superposition, be an integral of massive states. If you try to write a conformal field theory state, eigenstate, in terms of Poincare eigenstates for a standard quantum field theory, you get a superposition, just like you do in quantum mechanics. Quantum mechanics. And it is like this integral that kind of removes the scale from the system. But you still have massive modes in this sense. Alright? And the reason I'm insisting on this is because you read things like this in articles, and so it's important to know from the start what they mean. Because if you do not know, then you keep thinking, okay, there are massive particles in conformal field theory, so it doesn't set on the scale, so you keep going in a loop, you'll be confused.
So I'm just mean that the states cannot be, these massive states, they cannot be localized in a compact region. Because I don't know, I think
the particles on the rise. The particles on the rise.
So it's something localized that travels. So if there are no particles, you can't find states like this.
Yeah, we don't have wave packets.
We
don't have wave packets. We have other things that will be localized. We will come to that in another lecture. And I guess that is Basically.
But why do people keep saying this? That there are no massive particles? When someone
There are no massive particles.
yes,
But more because you cannot have particles on them.
says that, I imagine that there would be massive particles, but there are no particles at all.
Okay, from this I'm excluding a trivial theory. Say if you take pure QED, I said that QED is not conformal invariant, but if you take just pure QED, forget about any fermions and you just have the photon, it is conformal invariant. You just have the photon, but it doesn't do anything. It's a free theory, it's trivial. There is in fact a theorem by Weinberg that proves that massless particles in conformal field theory are necessarily free, so they decouple. So if you write in conformal field theory, okay, you might have massless particles, but they will be free. So I'm excluding this possibility from this argument. And then you could build up symmetries and so on. Okay. Weinberg, yes, even Weinberg.
Weinberg, Witten? No. Because I heard of a theory
Yeah,
by
yeah.
Weinberg and Witten.
You're probably talking about another theorem by them. But this theory too, what you're talking about is probably, what you have in mind is probably the theorem that says you cannot build a graphite as a composite particle from. This is another theory. This is a theory that also started with Witten. Witten looked at explicit, I guess, propagator for a scalar in a conformal field theory, and then he concluded that if you have massless scalars, then the theory will be free. But he was looking at the exact propagator explicitly. And then what Weinberg did, Weinberg took this observation and generalized it for any fields of any spin without the need to actually compute the propagator. It's just a theory about representations of the group. I can probably prove this in the next lecture when we have the conformal algebra. It's not hard, it's like a few lines. Okay? And just to close this motivation, another fact is that someone may be wondering how can conformal field theories be consistent with the Coleman-Mandula theorem. Everyone knows here what the Coleman-Mandula theorem is? No? The anyone who has studied supersymmetry? Yes, let me put this here. The Coleman-Mandula theorem states that the maximal symmetry of space, or space-time if you will, is Poincaré symmetry. Otherwise, if you have a higher symmetry than the Poincaré symmetry, you have a trivial theory. Trivial here means just a free theory. Right? This is always one of the first things that we talk about in supersymmetry courses, because in supersymmetry we introduce more symmetry to space-time. And the reason it works and you have non-trivial theories in supersymmetry is that you avoid one of the hypotheses of the theorem. Namely that you introduce fermionic generators. Right? They suppose that, to prove this theorem, they suppose that your symmetry group has only bosonic generators. If you introduce fermionic generators, if you introduce Grassmannian generators, then you can avoid this hypothesis and the theorem doesn't apply, so supersymmetry furnishes non-trivial theories. And the reason why conformal field theory avoids this theorem, see, we introduce space-time symmetries here. We introduce scaling and SCTs. So you could think, okay, so every theory is going to be trivial because of the Coleman-Mandula theorem. But another hypothesis here is that they suppose the existence. It's the hypothesis. the supposed existence of S matrix. And I just argued that in conformal field theories you cannot have S matrix. So that's how you avoid the fundamental theorem for the CFTs. And you see it works, because if you have, again, a free conformal field theory of massless particles, then you can indeed put it as an S matrix, but it will be trivial, okay, not interacting. It is an anomaly according to the Weiman's theorem, everything just fits. Yeah. Alright? That's how they proved that it will be true. They computed they showed that the S matrix would be just the identity. Alright? If you enhance the space and something. But if you do not have the S matrix, then you avoid the theorem. So the message here is, we're going to study conformal field theories, and they, in general, be interacting conformal field theories of massive modes, but we cannot actually measure in mass, of course. But if you insisted on thinking about a bit about the Poincare representation from the conformal field theory, there will be like this continuum of masses, right? And you read this a lot in the literature, so that's why I took this, the first thing that I did was this, to clarify what they mean by this, so you don't get confused. It confused me a bit, actually a lot, when I was starting to study this.
This supposition about the existence of X matrix, so it's basically that you can have asymptotically.
Yeah.
This is that you can asymptotically your theory is free, no?
Yeah, if you suppose that S matrix exists, you suppose that your interactions die in the asymptotic region. But then you clearly have two different scales. You have a length scale or a time scale, what you imagine is for the thing that where your theory is free, and somewhere in between they interact. So this break scaling varies. Right. In a conformal field theory, you cannot have things like that. Right? Okay. Any questions? We will start actually with some more rigorous calculations here. No questions? Basically, all I said here can be read in the introduction section of all these, I don't know, all these references here. They usually have, at least for the first two, the lecture notes by Qualls and Rishkov, they will give you examples of conformal field theories, and they will argue that you don't have particles. They will just, if you want to read more about it, you can read in the introduction, those are lecture notes. And then, well, examples of conformal field theories that we know are example. Classical conformal field theories. Maxwell theory, classically in 4 dimensions, is conformal. If you move away from 4 dimensions, Maxwell theory is not conformal, and the reason you'll come to understand eventually. You have, again, if you have classical theory, you don't have harmonization, right? So if you write down any classical Lagrangian that do not have any dimensionful parameters, doesn't have mass, doesn't have any dimensional coupling constants, then you have scaling variance. Quantum mechanics is another story. You can have anomalies and so on. It's a much more subtle subject, where scaling, the classical scaling transformation carries over to the quantum theory. An example of interacting classical conformal field theory would be classical Yang-Mills theory. Alright, because you have tough interactions between the gauge particles. In Yang-Mills, you don't have for QED, but for QCD you have a classical QCD with only gluons. You do have classical scaling variance. So we start with the conformal group here. I wrote already there in the I raised. For conformal transformation, we have this transformation log for the metric. It gets alright. And this is just a special case of it's just a special case of a diffeomorphism. This is what you see in every general relativity course, just an arbitrary change, an arbitrary diffeomorphism. Diffeo for short. And in a conformal theory, it's just a special case of a diffeomorphism. And yeah. So we're interested in studying, like we do in every area of physics, we're just like going to look at the infinitesimal transformations. We're gonna do x mu equals x. We're going to look at infinitesimal transformations. Why? Because by looking at infinitesimal transformation, we can find the underlying algebra of the conformal group. Okay? You can see trivially that this indeed furnishes a group, because if you do two scaling transformations, you can just do one scaling transformation by combining the scaling factors. The other transformation is just like Poincaré transformations. You could have an inverse scaling transformation that undoes previous conformal transformation. So we have all the group properties. Alright? Okay. So, has anyone here just studied general relativity? Yes, no? Yeah. Okay, so you know when you make for general diffeomorphism, your metric changes as you have the Killing equation, right? Just let me check how did I actually write this up here. Just it's missing the let me. Instead of writing the delta here, okay, it'll be good because I can fix. Sorry about this. Okay, up to here we're talking about the general metric. But for now on, we're gonna do conformal field theory in flat space. So we'll be studying conformally flat field theory in conformally flat spaces. Alright? And this is the Minkowski metric. Sometimes we'll do a big metric and now denote by delta mu, like this. Alright? And then since I don't have G here anymore, just erase this prime. This would be this would be the infinitesimal version of this guy here. If you just take this, plug it into here, and work out to first order in the infinitesimal parameter, then you'll end up with this expression. It's the infinitesimal transformation of the metric. It's the Killing equation. Now I will impose that this transformation be an infinitesimal conformal transformation. So on this side, I will just write. And since we're doing studying conformally flat spaces, it will be, let me move here. So let me do one more step here. Are you actually looking to meet this equation here? I'll probably do that. Over F. Alright, I just put these guys together and call the F, like for simplicity. Okay, so we will start from this equation to determine the most general form this epsilon mu of x can take for this to be a conformal, infinitesimal conformal transformation. First thing we do is we must determine what this f is. For this, we just take the trace of this equation. We just come here and multiply this equation by epsilon mu on both sides. Alright? We're just tracing the equation. So here we end up with the mu, epsilon mu, two times this. So we have I'll just write with a dot, okay? And here, if we in the dimensions. If we're seeking at the dimensions, then the metric contracted with itself just gives you d, the number of dimensions. Alright? So we have f of x is 2 over d is divergence. Okay, any questions? And this, we're going to make a remark here. Before the remark, let's put this back here. We end up in this equation. df is just this. Okay, now comes a remark. If we have a Euclidean two-dimension equals to space, then these equations become you have, for example, the mu equal nu components. They will furnish the same equation. It's going to be this equation. Say 0 equals, because the d will cancel, right? So then two dimensions. Actually, sorry, it's 0. This. And if you look to mu different than mu we have, this set of equations. These will be the set of equations in a Euclidean two-dimensional space that characterizes conformal transformation. Anyone? You want me to do this explicitly? Just plot d here. This factor cancels. Then just open this up. This metric drops because it just be Euclidean, the identity. So we have this set of equations, but this is precisely the Cauchy-Riemann equations. So this is the reason why two-dimensional conformal field theory is much more special than higher dimensional conformal field theory, because this will imply that any complex, any automorphic, monomorphic, or whatever you wish, transformation will generate conformal transformation. So the conformal group can be in two dimensions is infinite. So we have infinite symmetries, we have infinite constraints, and that's why in 2 dimensions we have the conformal symmetry is much more powerful, and we can, in a lot of cases, completely solve the theory in 2 dimensions. Okay, so because of this, that's the reason we separate 2-dimensional conformal theories from higher dimensional. And we're gonna come back. Everything I talk from now on will be for d bigger than 2 dimensions, and we'll come back to 2 dimensions in the second half of the lectures. And the reason is everything, basically, all the concepts that show up in higher than 2 dimension, d bigger than d higher than 2 conformal field theory, show up in 2-dimensional conformal field theory. But then in 2-dimensional conformal field theory, we have extra concepts, extra definitions. So if we start by high-dimensional conformal field theory, we can see more cleanly what are these concepts, and when we move to conformal field theory in d equals 2 dimensions, where we can actually do way more computations explicitly and things get more bit of a mess, then at least we already know exactly what we're doing and what those computations do. Okay? So everything from now on will be through the remark. I will consider d higher than 2. And we will see what are conformal transformations in this case. So we will just keep playing with this equation here. The next thing to do is, again, remind you, we want to determine the explicit form. We want to solve that equation for epsilon. That's basically what we want to do. And to find a solution, there is a kind of, if you study GR, there is a kind of a pretty unknown procedure. It's pretty straightforward. You do some steps. You start from this equation. Say let's call it 1. Start from 1. And take another derivative. So we'll have alright. Now we produce 2 more equations by cyclically permuting these indices. We write 2 more equations. So they're going to be alright. This is, for example, the thing we do, the method to find the crucible sign as a general relativity. What we'll do now is just we'll subtract the first equation from the sum of the other 2. So we'll sum these 2 equations and subtract this one. Okay? And you just go through the algebra, and what you find is we end up with this equation. basically you see that this term will cancel with this one, and this one cancel with this one. So we end up with 2 times these guys, alright, because I have new here. So I end up with 2 times this guy, and from the other side of the equation you have 2, so the 2 cancels, and end up with 1 over d. End up with this equation. And we'll save this equation for now. But now we're gonna do just one more thing. We're gonna take from this equation, we're gonna take divergence. We're gonna take the whole. Because here will produce the arounds dot epsilon, which is the same thing we have here on the side. And when we do this, we find this equation. So what this equation is telling us is we have 3 derivatives here, right? In each of these terms, we have 2 here, plus 1 here, and 2 other derivatives here. And this gives 0. So the solution of this equation, this equation is telling us that the solution of this equation must be at most quadratic in x, right? Because the third derivative vanishes. So we'll have something like this. Alright. Any questions? It's just the procedure to solve this equation in this sense. Alright? So this comprises all possible infinitesimal conformal transformations. And we will still come back to this. The first contribution is just a constant, right? The constant vector. So to what kind of transformations will this correspond? Translations, right? So, mu translations. They have the scaling factor will just be 1, right? It's just a concurrent transformation. Right? Transformation have scaling factor 1. They preserve lines. Now we come to the second contribution. We have this 2 tensor here. We can write this tensor. We can decompose it in 2 components. We have a constant lambda. That's a mu, which is symmetric, and we have an anti-symmetric part. Would be you could write some constant alpha here with an anti-symmetric part. Principal can be symmetric. This guy, does anyone know what this guy describes? The antisymmetric part. It is a linear contribution in x, and it is unsymmetric.
It's a Lorentz transformation.
Lorentz transformation of rotations. Right? So we will have this set describing the rotations.
So you're restricting yourself to the proper orthochronous group.
Yeah. When we do infinitesimal transformations, we already implicitly restricted to that component. There will be conformal just for as for the Poincaré group, we have the discrete transformations P and T, and we have one more discrete transformation for the conformal group, but it's not. We are not finding that transformation from this. This is the inversion transformation. We'll talk about that too. This will be really important. But for now, we just study the continuous transformations that connect the identity. Okay. This part, the lambda atomic group. Okay, so we already identified the Poincaré symmetries here. The Poincaré subgroup. Alright, we already found the translation and the rotations. Also have a scaling factor 1. Anyone wants to take a guess what this transformation is? Scaling. The way to see this, if you just take this transformation, then just take this component. If you plug it back here in this formula, you have that your x prime is going to be x and lambda x, lambda are constants. Right? So this is just a scaling transformation. Okay. So this describes scalings. Some people call these dilatations, for example, but I prefer the name scaling because dilatation gives you the idea